to redo this twice. All right, so let's look at this particular example, this one that's labeled 16.7 here. So you've got a random sample of size 3, and you've got two different statistics here that are giving you estimators of the population, and it's asking which one's more efficient. So when it's asking you which one's more efficient, you can do a calculation of that relative efficiency, or you can just look at the variances of the two and compare them and see which one's smaller. So it claims that they're both unbiased estimators. Let's check and make sure that Y really is unbiased. So remember, we just want to make sure that the estimator being unbiased means that it's giving us the expected value, gives us the parameter that we're looking for, which in this case I believe is the population mean. So we're going to do the expected value of the statistic that we're computing. And then, of course, we can pop out the 1/6. It's just a constant. And then break up the expected value over the sum. And in those second two terms in the sum, we can pull out the constants as well out of the expected value. So we get that expression. And now each of the x's is coming from the same population. So the expected value of each of the population, or excuse me, each of the x's is the same as the mean of the population. So we really do get mu out of this when we simplify. All right, so now let's check our variances and see which one is more efficient. Well, since the population has a variance of sigma squared, we know that the variance of the mean, the sample mean, is sigma squared over n. We already know that from work we've done previously. And in this case, since we have a sample size of 3, I can go ahead and plug in 3 for n and get sigma squared over 3. For y, we've got this longer statistic here. All right, so we know that we can pull out the constant, but of course when we pull out the constant we have to square it when we pull it out of the variance. I'll do this in a couple of pieces. Then the second part is I need to break this apart over the sum, and we know that since we're doing a random sample, each of the x of i's is independent from the others, so I can just break apart the variance over the sum and I don't have to worry about any covariance issues. And then just like what we did when we started this part, I can pull out the constants out of the second two by squaring them. And then each of the variances of the x of i's are all sigma squared. So we get 14 over 36, or what is that, 7 over 18? So we get 7/18 sigma squared here. And now if we compare the two, 7/18 is a little bit bigger than 1/3, which is 6/18. So the variance of x bar is less than the variance of y. So x bar is more efficient. It's not unlike the example that we did at the end of class last time. Just instead of having that increasing thing up to n, it stopped at 3 in this case. Questions on that one at all?
Dr. Joe, can you explain why you used the equation given in the problem for the expected value of x bar, but then the variance of y?
For which part again? I'm sorry.
Like the equation that they give, like the x1 plus 2x2
Yes.
plus 3x3 over 6.
Yes. So, what we're trying to compare, well, the first part I just did the expected value of y because I wanted to make sure that the problem said it was unbiased, that both of them were unbiased, and I was just checking in this first part to make sure that it really was, that y was really unbiased. We already know that the expected value of x bar is unbiased. We know that the expected value, we know that x bar is unbiased for the mean, that the expected value of x bar is mu. This first part was just me checking to make sure that y was unbiased as well. The second part was me actually going through and calculating the variances for the two statistics, the x bar and the y, and seeing which one had a smaller variance. That help?
Yes.
Okay.
So then how do we know on your variance of y, when we got it down to the variance of each of the x's, how do we know that we can substitute the sigma squared in for those?
So remember that we're doing the random sample from the same population. So x1 and x2 and x3 all have the exact same distribution as the underlying distribution. So we know the variance of each of those is sigma squared.
Okay.
Since the population you're drawing it from has a variance of sigma squared. When we deal with the random samples, we treat them like they're independent and identically distributed. That's where we know that they all have the same variance.
Okay.
Other questions? Okay, well, let's do the next one. Same idea here. So this one's a little bit more, it doesn't have us doing a lot of computations here because we should already know the distribution here that the x's are coming from. So in this particular case, we will give us the PDF, and we should recognize this, I hope we recognize this as the PDF of an exponential distribution, right? So we already know that for this distribution, the mean is theta, and the variance is theta squared. Okay, so the first part asks, are the estimators just using the first thing in your sample, and using the sample mean, are those unbiased? And then it asks which one's more efficient. Well, again, just like what we just mentioned a minute ago, since this is a random sample, each of the individual x's if you just look at the distribution of each of the individual x's, they all have a distribution that is exponential. So the expected value of x1, since it's an exponential distribution, really should be theta. And we know from work we've done before that anytime we have a sample mean, we also know that the expected value of the sample mean is the same as the expected value of the underlying distribution. So both of those are unbiased estimators. So this tells us that x1 and x bar are unbiased estimators for theta. So to figure out which one's more efficient...
how do we know that the expected value of x1 is theta again?
So again, each of your x sub i's in the random sample has an exponential distribution in this case. Because again, we're doing a random sample. So if you, instead of doing a random sample of n, think you just did a random sample of 1. Well, if you did a random sample of 1, that's just going to be the same variable that you're talking about as far as your distribution. So each of these has an exponential distribution. If I can spell distribution. With mean theta. So that's how I know that x1's expected value is theta, because it has the same distribution as the underlying distribution. And since we also know that it has an exponential distribution, I know that the variance here is sigma squared, because it's just one of the sample pieces, right? So its variance is just sigma squared. But if I want the variance of the sample means, that's going to be sigma squared over n. Because remember, when we do the variance of the sample means, it's the variance of the population divided by the sample size. So as long as n is bigger than 1, x bar is more efficient. I mean, if n is equal to 1, that's the same. But so as long as n is greater than 1, x bar is more efficient than the x1 is. Which, I mean, if you think about what this is saying just in words, this makes sense. You're going to, basically, the idea behind efficient estimators is that, on average, you want to be closer to the true value. That's the whole idea of being efficient. I want to, from a probabilistic standpoint, I would like to be close to the true value of the population. Well, on average, you're going to be closer to the true value of the population mean if you're going to use an entire sample and take the mean of the sample than if you just take one element from the sample and say, oh, that's the mean. Does that make sense? I hope.
I'm not gonna lie, I'm a little confused because in the last one we said the x bar is more efficient.
Yep, that's what we're saying here too, right?
Less than.
Oh, well, so, I mean, that's the same idea, right? The variance of the x bar here is less than the variance of the x1. So that's what makes it more efficient.
Oh my god, I'm such an idiot.
No, it's all right. I'd rather you ask than not. I mean, I'd rather it make sense.
So we always get what the mean and like variance are based on the distribution that they give us.
Yes, you'll always get that. Yeah, you always have the mean and the variance, but based on what type of underlying distribution it is. Either they tell you what the distribution is, or they just say you're trying to estimate the mean, or you're trying to estimate the variance, those kind of things. And in particular, you have to have some sort of way to at least represent the variance, because if you're trying to talk about efficiency, it's in terms of the variance. So there must be some way to have some sort of I'll say a baseline to try to get that measurement from.
Okay, and then the variance for x bar is always going to be over n.
Yeah, remember that was our central limit theorem stuff from last semester. That when you do the expected value of x bar is always whatever the mean is of the distribution, and the variance of x bar is always what the variance of the distribution is divided by n.
Okay, yeah, that makes sense.
Okay.
And then, just to clarify, this may be a stupid question, what x bar is your distribution, like if you take a lot of samples and it's their distribution of their averages?
That's exactly right. Yes, that's exactly right. All right, let's do another one here. If I can get my page to scroll. Maybe. Here we go. All right. So here's another one that's asking about efficient. Which one's more efficient, and can you find another one that is actually even more efficient than the two that they give you? So this one, it's asking first if they're unbiased. So checking whether or not they're unbiased is a matter of doing their expected values. So if we do the expected value of lambda 1, well, again, we know that expected values, I can pull constants out and break them up over sums. That's not a 1/2. So I get 1/4 of the expected value of x1 plus 2 expected value of x2, and then plus expected value of x3. When we break that up. And now again, this is one where they give you the PDF, so we should be able to recognize what kind of random variable this one is. And that is a Poisson. I guess I should technically say PMF since it's a discrete one, but that's certainly Poisson, right? Because we got the lambda to the x and e to the minus lambda in there. So we know that the mean for the Poisson and the variance for the Poisson are both lambda. So we might need both of those pieces of information here. And we certainly need one of them right now. Because now, since each of these is randomly selected from the population, I know that if I do those distributions, each of those distributions should be the same as the underlying distribution. So each of those expected values will be lambda, and we certainly do get lambda for this one. If we do the second one, same idea. I mean, exactly the same idea, just with different numbers. Oops, forgot my expected value here. So again, pull out the constant from the expected value, break it up over the sum, and then pull out the individual constants. So doing all that at once. And then again, each of the x sub i's has the same distribution as the population. So each of them is Poisson. So the expected value is lambda, and it's again not too hard to see that that's going to equal lambda. So the answer to the first question is yes, they're unbiased. So now we want to check their variances. And we're going to do the same kind of thing that we just did in the previous. Okay, so when I take the variance of this first piece, I know that the first thing we're going to have to do is pull out that constant. When we do that, we have to square it, right? So that'll be 1/16, and then the variance of the x1 plus the 2x2 plus the x3. And then again, since it's a random sample, each of these are independent, so I can break up the variance over the sum. And then in that middle term, again, I can pull the constant out of the variance, but I'll have to square it when I do. So this will be 1/16 times the variance of x1 plus 4 times the variance of x2 plus the variance of x3. And now again, each x sub I has a Poisson distribution. I almost said Poissonly distributed, which doesn't make any sense. Each one has a Poisson.
That sounds right to me.
Does it sound right? Okay, it's Poissonly distributed. Okay. So each of the variances is lambda here. So we would have lambda plus 4 lambda plus lambda. So we get 6/16, so that is 3/8 lambda. And now let's do the same thing for the other one. We'll have 1/81 when we first pull out that 1/9. And then again, each is independent, so I can break up the variance over the sum. I have no idea what that was in the background. The variance, I can break it up over the sum, and then I can pull out the constants out of each one. So I get 16 variance of x1, 9 variance of x2, 4 variance of x3. So then, we know that each of them is Poissonly distributed again. So I get a lambda for the first one, and a lambda for the second one, and a lambda for the third one. And what do we get? 29 over 81 in that case? All right, so now I just need to figure out which one's smaller. Let's see here. Of course, they give us denominators that don't match very well, but that's okay. So, what would we need to do? Multiply the 3 by 81 and the 29 by 8 to compare it. So, this one would be, what, 243 over whatever 8 times 81 is. And this one, if I multiply this one by 8, you get 2 and a 7. So 16 and 7 is 23 over 8 times 81. So it looks like lambda 2 is more efficient than lambda 1 as the smaller variance. So lambda 2 is more efficient here. Is that part okay? See?
Yeah.
Let me put something in the chat. LOL. Okay. All right. So.
I can hear when you screamed into the mic really loud somehow for like 1 second.
I did? That's weird.
Something must have been like scratching and it like screeched.
Oh, really? Oh. Wasn't me. Sorry.
It wasn't pleasant.
But I would imagine, yes. Sorry. All right, so the second part of this asked for, can you find an unbiased estimator that is even more efficient than these two? Well, the one unbiased estimator that we know typically is a good one to use is the sample mean, right? So if I do the variance of the sample mean, in this case, that would be the variance of the distribution over the sample size. So in this case, we get lambda over 3. And, let's see, now I need to do more multiplying again. Stop it. So, let's see, what do I need to multiply the 3 by to get the right denominator here? I'll need to multiply it by a 27 and an 8. Maybe it was something in the background that you keep hearing because that was loud. If I do the 27 times 8, well, certainly that's going to be less than when we did the 29 times 8 there. What do we get, 216? If I did that right? So if I do 216, this is the same thing as 216 over that 8 times 81. So then the x bar will be even more efficient than the other two, since it has an even smaller variance. Questions on that one?
So would you say then that your x bar is more efficient?
Yeah, the x bar is more
The
efficient.
variance of x bar is more efficient.
You say the x bar is more efficient.
Okay.
Yeah, you say the estimator is more efficient in that case. Okay, so let's talk about a new definition here. so that we can compute this particular one here. So, pardon me. So, we're talking about what's referred to as the mean square error. Oops. Or in some sense, the mean square error is it's a measure of how bad an estimator is, if you will, on average. How bad the error is. So this is the expected value of the difference, the square of the difference of the estimator is from the true value. So this is how we define the mean square error. Notice that we wouldn't necessarily want, well, we don't want to leave off the square in the case where this is a an unbiased estimator, because you'll just get 0, because the expected value of theta hat would be theta. So this wouldn't be a very meaningful statistic if you're doing this for unbiased estimators, because you're trying to figure out how bad of a guess is this estimator. So we want some measurement of how bad it is. So the reason why we square it is to make sure that we don't have those differences. On the average, the differences end up canceling each other out. It's the same idea when we did variance, right? We didn't want to just do the expected value of the difference of each individual point from the mean, because on average, when you do the expected value of that, you just get 0. So same idea here. When we do the sum of those deviations, we would get 0. That's why we square it if we want to measure of something about the error idea. So the reason why we call it the square error is because we're squaring it, and the mean is coming from the fact that we're doing an expected value. So that's why this is called mean square error. Now, typically, you're not going to want to calculate your mean square error by using this formula, so we'll have a nicer way to do this, much like we have a nicer way to compute variance. So to get to that nicer way, let's derive this real quick, and then we'll come back to this example. Okay. So let's first, before I square this out, let's first add and subtract in. I'm going to make this a square bracket because I'm going to have lots of brackets in here. Let's add and subtract the expected value of theta hat here. All right. So then I want to square this, but I want to square this by leaving this like it's a single term and leaving this like it's a single term. Okay? So when I expand this out, I don't want to expand out those two particular differences that we have there. All right, so when you expand this, when you FOIL this one, the first one will give you a theta hat minus expected value of theta hat squared. You'll also get an expected value of theta hat minus theta squared. And then, of course, what I'm missing are the middle terms. So I'll have a plus a 2 times theta hat minus expected value of theta hat times expected value of theta hat minus theta. Oops, forgot to put this there. Bracket. Okay, so now let's break this into pieces. First piece, I have expected value of theta hat minus expected value of theta hat squared. And in the second piece, we have expected value of expected value of theta hat minus theta squared. And then over here, I've got a couple of constants that I can pull out. Once I compute the expected value, this is a constant here. This is also a constant, and of course the 2 is a constant. So this comes out as a 2 and there's an expected value, of theta hat minus theta. And then I have expected value of theta hat minus the expected value of theta hat. Lots of words, I know. All right, so
Dr. Joe?
yeah.
How is that last term a constant again?
This last term?
Yeah.
Okay. Once we compute expected value of theta hat, it's typically in terms of the theta, but it's already been computed in expected value. There won't be any x's left in it because the theta hat should be a statistic based on your sample. But when I do the expected value, there won't be any x's left in it. So this, relative to computing expected value, this thing will be a constant. And your parameter is also, the theta is representing the constant parameter of the population. So when I subtract them, they're both constants, so I can pull them out in front. That's why. Because when we've computed the expected value here, that makes it a constant relative to computing expected value.
Okay. So then what's the difference between the term before it, since it has that expected value of theta hat?
Oh, we're going to come back to that.
Oh, okay.
I just didn't do that. I just didn't do that one yet. I'm going to come back to that one.
Okay.
Because there is no difference between it. You're exactly right. I was coming back to that. Sorry, I didn't mean to confuse by doing it in one and not the other.
Okay.
Yeah. So
Sorry for jumping the gun.
No, you're fine. No, I wanted to break it into three pieces because we want to recognize what each of the three pieces are. So you're right. You're good. That's a good catch. Thank you. All right. So let's look at this last piece here. The one I'm going to underline in red here. Now again, I have expected value of a parameter minus what its expected value is. Or again, this is a constant as far as expected value goes, so you can break up the expected value over the difference. You end up with expected value of theta hat minus expected value of theta hat. So this term is going to turn out to be 0. So this whole term goes away. So I'll say that again. I'll just write it up here. Expected value of theta hat minus expected value of theta hat is expected value of theta hat minus expected value of expected value. But when we do expected value, it turns into a constant. So this is just expected value of theta minus expected value of theta, which gives us the 0. That's why this one goes away. All right, so now back to the second term. As Morgan already noticed, this expected value of theta hat minus theta is a constant. So when I square it, it's already a constant. So essentially, I can ignore the expected value piece because expected value of a constant is the constant. And now, if I look at this formula, if I look expected value of theta hat minus theta, we have a definition for that. That's the bias. So this second piece is just the bias of theta hat squared. So that second term, and what we just expanded all out, is the square of the bias. And now in the first one, this is a definition. I'm taking a random variable, subtracting its expected value, taking a random variable, subtracting its expected value, and squaring it and doing its expected value. That's the definition of variance. So when you actually compute mean square error of a statistic, you do the variance of the statistic and add the square of the bias. Okay? So now I can go back to that original problem armed with this formula and answer the previous question. So in this particular one, I'm going to write the formula back over here so we can actually reference it. The mean square error is the variance plus the square of the bias. So in order to be able to compute the mean square error, I need to know those two pieces. I need to know the variance of theta and the variance of theta hat and the bias of theta hat. Well, we know from what we've done before, we can compute the variance by doing the expected value of the variable squared minus the expected value of the variable quantity squared. And they tell you in the problem here that expected value of theta hat squared is 13. Expected value of theta hat is 3. So, and we get 13 minus 9, which gives us 4 in that case for the variance. We also have enough information for the bias. Remember, the bias is defined as the expected value of theta hat minus theta. So we get -1 in this case. So now we're ready to compute the mean square error. So in this case, we would have 4 plus -1 squared, which gives us 5. Once we had the formula, the problem was no sweat. Getting to the formula was a little bit of a work, but once we have the formula, the problem is just a matter of getting the pieces plugged in the right spots. Questions? Stunned silence, I hear. Okay.
Crickets.
Crickets.
No questions, Dr. Joe. Thank you.
All right, let's do another one. This one requires a little bit more thought. So this is a very, very interesting population. It only has the values of 1, 2, 4, and 9 in it. To figure out what to estimate what the population mean is, even though you could calculate it in this case. To estimate what the population mean is, you're going to take a sample of size 3 and look at the median of the sample. And in particular, you're going to do this drawing of the sample without replacement. All right. So it asks us to calculate the mean square error as an estimator. So that means that we have to figure out both the bias and the variance of the median of the sample. Well, let's think about what our possibilities are for the sample in general. So we're doing this without replacement. So if I'm going to do a sample without replacement, I've got 4 things to choose from, and I'm choosing 3. That means we're only going to have a possibility of 4 different samples, right? So you could have a sample of 1, 2, 4. You could have a sample of 1, 2, 9. You could have a sample of 1, 4, 9. Oops, 1, 4, 9. That's what I meant. And 2, 4, 9. So notice that the median of the first 2 samples is 2. And the median of your second 2 samples is 4. So if you think about doing this over and over and over and over and over again, you would expect that half of the time you would get a median of 2, and half of the time you would get a median of 4. So that tells me that my expected value of y should be a half times 2 plus a half times 4. Again, half of the time we get a 2, a half of the time we get a 4. So we expect the expected value of y here to be 3. We can also calculate the mean of the population. I'll just refer to it as mu here. That's certainly not a hard thing to calculate. If I add it up and divide by 4, I get 4. So now we can calculate our bias, because that's one of the pieces we need to know for mean square error is the bias. I get -1 like in the previous example. So then I need to know the variance. This one's not bad to compute either, because again, we know that half of the time the value is 2 for y, and half of the time the value is 4. So I can compute expected value of y squared pretty easily. Half of the time it's 2, so I would take 1/2 times 2 squared. And half of the time it's 4, so I would take 1/2 times 4 squared. So I get 2 plus 8, I get 10 there, if I did that right. So the other piece of information that we need to know is the variance of y then. So the variance of y here is going to be expected value of y squared, which is 10, minus expected value of y quantity squared, which is 3 squared. So we'll get 1 for our variance in this case. And so now we're ready for mean square error. Remember again, that's variance plus the bias squared. So we'll get 1 plus -1 squared, so we'll get 2 in this case. They made the problem a little bit easier on us in this case because they told us the samples were being taken without replacement. If your sample was done with replacement, you would have had a lot more samples to have to go through. Because if you're doing the sample with replacement, you'd have 64 possibilities for your samples. Because you have 4 choices for each of the elements that you picked up. And then you'd have to worry about order. So then you'd have 64 total possibilities, but some of them would look the same. So you'd have a big pain trying to calculate all of the medians in that case. Not impossible, just more of a pain. Questions on that one? We okay with that one?
Yeah, I think so.
Okay. All right. Let's do this one. Why not? Because it's asking us to do the mean square error in a couple of different parameters, the phi and the psi. So they tell you that the beta is 2, and they want to know what the mean square error is of each, and then do the ratio. We have enough. Hopefully, we have enough information to do these. So remember, our mean square error is variance plus square of bias. Okay. So to get the bias, of course, we need to be able to we need to know what the expected value is. So let's look at the expected value of the psi and the expected value of the phi. Well, when we do expected value, you would add them up and divide by how many there are. So the sum of all of the psi's is 165. And there are 75 total. And, of course, I don't have a calculator, so let's see if I can get my phone here. 165 divided by 75 gives me 2.2 for that one. Let's do the same thing for phi. We would have 147 over 75. That gives me 1.96. So then I can calculate the bias in each of these. Remember, we're trying to use these as an estimate for beta. So they tell us that the beta is 2. So the bias in psi will be 0.2. The bias in phi will be negative. That was interesting. Not sure why it minimized that. It'll be negative 0.04. All right, for the other part of mean square error, we need the variance of each of these. And of course, the variance is expected value of the psi squared minus the expected value of psi quantity squared. So we know each of these as well. The first part will be 312 over 75, because they tell us that the sum of the, oops, sorry, not 312, 375. I looked at the wrong one. They tell us that the sum of the size squared is 375. And we already did expected value of psi squared. So if I do 375 divided by 75, and then minus 2.2 times itself, I get 0.16 here. And now I want to do the exact same thing for phi. Now it's 312 over 75, and then we'll subtract 1.96 squared. So 312 divided by 75. 312 divided by 75 gives me 4.16, and then I need to subtract the 1.96 times itself. Here I get 0.3184. All right, so now for the last pieces, we want the mean square error. I'm not going to bother doing the division, but if I want the mean square error for these, oops, this is going to be your variance of phi, psi, is what I'm working with. The variance plus the square of the bias. So we've got 0.16 plus the bias is 0.2 squared, and that gives me 0.2. Over here, for the mean square error of phi, same formula, just with using the numbers for phi rather than the numbers for psi. And then, of course, I said psi, so I wrote a psi. Psi. Variance of phi is 0.3184, and bias is negative 0.04, but we're going to square it anyway. And here we get 0.32. So then at the end, to do the ratio that it asked for, you could take the 0.2 and divide it by the 0.32. Lots of numbers we were plugging in there quickly, I know, but the formula didn't change, and it's the same stuff that you've done before with figuring out variances by doing expected value of the variable squared minus expected value quantity squared. Questions on that one? Or questions about anything else at all? Are we good?
What's that notation they're using for mean square error?
What's the note? They're talking about the mean square error of the estimator with regard to the parameter. So it's just got the subscript in there for that. It's specifically specifying what the parameter is that you're trying to calculate the mean square error of. Only because in this case there's 3 different Greek letters flying around, so making sure people know which ones are supposed to be which. Other questions at all?
Got it.
Are we good?
Good.
Good? All right. Well, have a good day, everybody, and we will talk to you next time.
Thank you.
Bye.
Bye.
Oh, crud.